So we've spent a little bit of time talking about the origins of chemistry, including some contributions of the ancient Greeks, some contributions of the alchemists, and a little bit about the contributions of Jabir and the so-called father of modern chemistry, Lavoisier. Let's jump forward again a little bit, not too much from Lavoisier, maybe 50 years or so, and we'll go to England and we'll go to the time of an individual by the name of John Dalton. Now, John Dalton was what was known at the time as a pneumatic chemist, which meant that he was a studier of gases. Many of his contemporaries, and even those even 100 years before him, were also known as pneumatic chemists. It was the period of time where gases were being thoroughly investigated by individuals such as Robert Boyle and Gay-Lussac and Charles Priestley. A large number of individuals were doing gas phase experiments. But John Dalton was also a premier educator and statesperson for the spreading the gospel of chemistry itself. Dalton is revered in many regards, in particular as a communicator. He established several schools that people could attend, not just for science, but for education in general. Dalton was a long time lecturer to not only the academic community, but also to the public community. You see, what went on in the early 1800s was that, particularly in the large urban settings, scientists of the time would hold open, probably for profit. I'm not going to claim that it wasn't, but they would hold open lectures where the public would be invited and they would talk about the latest advancements in science. Believe me, Dalton was not the only individual who did this. Many of the prominent scientists of the time would hold essentially like rock shows, if you like, where they would purport the latest advances in science, maybe give some demonstrations of things that could be shown on stage, and then discuss what the latest theories of these certain phenomena they were showing were. So Dalton, being a great communicator in chemistry, is given credit for what is known as the atomic theory of matter. Almost every chemistry book that you will encounter lists this as Dalton's atomic theory. Now, having said that, do I believe that these ideas were solely purported and expressed and championed by Dalton? The answer is no. I'm sure most of the hotshot contemporary chemists of the day had the same sorts of opinions on chemistry as did Dalton. Dalton was just, as I mentioned before, a good communicator, and so Dalton is generally credited with the so-called atomic theory mainly because of his ability to spread the gospel through his academic opportunities and even his public lecture opportunities. Just another interesting side note about Dalton. Not only was he interested in the area of chemistry, he was also interested in the area of climatology. He was like an early version of a weatherman, and he kept incredibly detailed records of the daily climatic condition in and around London. Everything including the temperature, the barometric pressure, precipitation levels, wind speeds, wind directions. And when I say he kept a record of this, he religiously kept a record of this for decades of time, not just daily, but we're talking for periods of year after year after year. He kept incredibly detailed records of all these conditions. Well, where that came to be very important was later when scientists were finally formalizing the ideas of conditions that cause weather patterns. They referred back to the detailed writings of Dalton to help them get data about the way weather patterns change with the seasons and how certain conditions lead to the behavior of the weather patterns. So his ideas on weather were also very important towards our understanding of how to interpret and predict the way the weather may come out a few days after what it is currently. This slide lists what is the summary in 4 bullet points, the so-called idea that is universally known in chemistry as Dalton's atomic theory. This is the premise by which modern chemistry this is sort of the foundation of modern chemistry. Everything kind of stems from these 4 bullet points. Now, once again, just let me say before we just talk a little bit about them, that even though Dalton is given full credit for this atomic theory, do I personally believe that he was the one who came up with this? I don't know. He probably had discussed ideas such as this with other contemporaries of the time, and many of them probably came to this same opinion. But as I mentioned in the last slide over and over again, it was Dalton's prowess as a communicator that probably landed him as the person in all textbooks who is given credit for these ideas. So again, remember that there had been previous ideas as to how chemistry was beginning to be formalized from just a utility that humans could use to better their lives into trying to understand the way that matter interacts with itself and with other forms of matter and ultimately forms everything that we have around us. So let's look at these 4 ideas and talk a little bit about each one. And then we'll have a little more to say as we go on with these concepts as well. But we begin with statement number 1 that says all matter is composed of indivisible particles that are called atoms. Now you might recall that the word atomon, A-T-O-M-O-N, had been introduced into the idea of material science by Democritus and then furthered by his student Leucippus way back almost 500 years BC. And they even used the word indivisible in Greek, which is shortened here to the word we now call atom. So remember, if you recall what I talked about after that occurred, an individual by the name of Aristotle, who was much more prominent and had much more influence, shortly after Democritus and Leucippus had proposed the so-called 4-element theory. And for a long period of time, people ascribed to the 4-element theory that everything was made from air, fire, earth, or water. And also then into the alchemy period, where there was all sorts of transmutation of matter attempted, all sorts of wizardry and deceptive, superstitious practice placed into this so that it was more of maybe a shyster or entertainment area than it was what we would consider to be a mature science. And then finally, after a few thousand years anyways, we began to really formalize material science and the understanding of matter in what we would now call modern chemistry. So it came back, if you like, full circle, back to the idea of Democritus and Leucippus that matter could be made of small indivisible particles called atoms. Then we see the second idea was that different elements, and they remember the word element had been introduced by Aristotle in his incorrect assessment that there were 4 elements, but this word has been retained as a building block name, a fundamental component of matter is an element, and an element itself is, if you have a tractable amount of it that you can hold in your hand and such, is a huge number of these individual building blocks known as atoms. And if you have a pure element, all atoms in it, according to Dalton's atomic theory, every atom in that element, or huge pile of them, that it has to be so huge because each individual atom is so small, so the huge pile of it is consisting of material of all atoms of the same type. So if you have a different element, it will be, of course, composed of atoms, but the atoms of that different element are different for each individual element. Each element has its own unique atomic form. Okay, then thirdly, he begins to really speak about chemistry. When you start to put things together in combination, and when you put things in combination, the transformation of matter is chemistry. That truly is, you're now doing chemistry when you're taking matter in one form and changing it into matter in another form. So 2 of the ideas that were placed in this were actually ideas that were really, if you really examine this closely, they came from Avogadro. And these ideas that come from Avogadro are that when atoms combine in definite proportions, they are forming the same compound. So what would be an example of that? Well, let's take combining carbon with oxygen. If I combine one carbon atom with one oxygen atom, I get a carbon monoxide. Well, if I want to make a larger pile of carbon monoxide and I take 10 carbon atoms, I would have to use 10 oxygen atoms because it has to be in a definite proportion to make carbon monoxide. If I take 1 million carbon atoms, I had better take 1 million oxygen atoms and combine it with those carbon atoms if I'm going to form that same substance, carbon monoxide. So that's the idea of definite proportions. Anytime you form the same material from a varying number of reactions, the combining elements are connecting together in a definite proportion. The remainder of idea 3 has to deal with when you're forming different compounds or materials. And that's when they combine. If you're going to form something different, it will combine in a different ratio. That's what they're calling a multiple proportion. So what would be the idea there? Well, if I, instead of taking 1 carbon per 1 oxygen to form this material carbon monoxide, what happens if I take 1 carbon and combine it with 2 oxygens? When I do that, I'm forming a different material than when I combine 1 carbon with 1 oxygen. And of course, 1 carbon with 1 oxygen, I'd be forming carbon monoxide. 1 carbon with 2 oxygens, I'd be forming carbon dioxide. The properties of carbon monoxide and carbon dioxide are incredibly different. Even though they're both clear, colorless gases, carbon monoxide is a lethal clear, colorless gas. If you breathe in enough of it, you will die, whereas carbon dioxide is not. So that is the concept of multiple and definite proportions. Definite proportions, you're forming the same material, and so the combining atoms have to be in the same ratio. And multiple proportions, if you're forming different materials, then the combining materials or the combining elements are must and must. When I say this, you can't possibly form different materials by combining the same things in the same proportion. Okay, so then finally, and probably the most powerful of all the statements of Dalton's atomic theory, is talking again about chemistry, and it's about really reaction in chemistry. And when you have a chemical reaction and what a chemical reaction purports is that materials are transformed from one form into another. Well, in that transformation of one form into another, the building blocks are conserved. At the atomic level, every atom which went into the materials that you begin with must somehow end up in the materials you end up with. So no matter is created or destroyed ultimately in the chemical reaction. Now it is transformed. It might have completely different properties, including its phase, including its shape, including its color, including its properties such as hardness or bendability or conduction of electricity. All these sorts of things may vary from the start to the finish, but the components that started from the original materials all must be represented in the final materials. So the atoms are not thrown under the rug of the universe, or atoms are not plucked out of thin air. They are just taken apart from the starting materials, rearranged and put together in a new form in the product materials. Turns out that is probably the most profound of all the statements made in Dalton's atomic theory. Well, we said on the last slide that there were 4 ideas in Dalton's atomic theory that basically form the gospel of chemistry. Well, what it turns out is that with some hindsight and now some more advanced knowledge than was available to Dalton at the time, what we now know is that 3 of Dalton's 4 ideas were actually incorrect. So let's talk a little bit about the incorrectness of Dalton's ideas. The first 3 of them, it turns out, have a little bit of, they don't really hold up under today's understanding. Now, of course, let's first say something about that. Dalton simply did not have the information that we now have, which has made us revise some of Dalton's original ideas. Let's also say that Dalton's original ideas were certainly a good starting point that got us going. And again, when more experimental evidence became available over the next 100 years, some of the ideas of Dalton had to be revised, not completely thrown out, but had to be revised. And what were those changes that are necessary? Well, the first one says that all matter is composed of indivisible particles called atoms. Well, we now know that there is subatomic structure. Atoms are made of building blocks themselves. And familiarly to you, the building blocks of atoms are the protons, neutrons, and electrons. Now, all atoms are built from these same protons, neutrons, and electrons, but put together in different proportions gives us different types of atoms. And then these atoms collected together can make an element. So, of course, there was no experimental knowledge that you could subdivide atoms at the time, because it took a lot of detailed investigation and finely adapted viewing apparatus and techniques that allowed them to understand that atoms themselves could be broken down. Well, really, if you want to get technical with it, we can't even stop at the subatomic particle level. There are actually subatomic particles well beyond, or well more fundamental than the proton, neutron, and the electron. There is, as a matter of fact, an entire periodic table of the particles that make up matter. These include probably familiar names to you, like quarks and leptons, muons, pions. There's just a whole host of things that can be put together ultimately to make matter what it is. Now, maybe as we have time later on, I can wax poetic to you about the nature of where and why we don't see these particles now. It really boils down to energy. You have to put a lot of energy in to allow these particles to live independent of one another. So maybe at some later time we will have a few moments to go into that. But under normal energetic conditions that we live in, there's no subatomic particles. They can't live free and independent of one another. There's no subatomic particles. Well, we actually can see those in an electrical current. We can see the separation of the charge from an originally neutral product. When we put enough electric potential across it, we actually can see something like that. But generally speaking, the reasoning behind why Dalton didn't have any idea about this was because at the energy that we normally exist, atoms are collections of the subatomic particles that aren't going to come apart. Okay, now let's look at the problem that Dalton had for his second statement. His second statement says all atoms of an element are identical. So if you have the element nitrogen, it's composed of a bunch of atoms. If you have a pile big enough to see in your hand, and every atom of that nitrogen is the same. And every atom of that nitrogen, if you have in your other hand a pile of helium, every atom in the helium pile will be the same as every other atom in the helium pile, but will be different than the atoms in the nitrogen pile. Well, it turns out that was close, but that is not right either. And the problem with statement 2 again goes back to the ideas of statement 1, where if you look closely at statement 1, atoms are actually divisible. You can break them down into subatomic particles, protons, neutrons, and electrons. So when you build the atoms of the same element, you can build them ever so slightly differently by altering one of those particular subatomic particles. Turns out that is the neutron. The positive and negatively charged protons and electrons are pretty much the same in every case of every atom of an element. However, you can build those same atoms with different neutral particles known as neutrons, and they will have exactly the same chemical properties, hardly unnoticeably different. The only differences that can be noticed when you have different isotopes that have different numbers of neutrons in the nucleus is that since they're heavier, they will move a little more slowly in a mixture of a whole bunch of atoms of the same type, so you can notice it that way. And it turns out in a magnetic resonance imaging experiment, if you have different numbers of neutrons, they will have different activity towards whether they're detectable in an MRI. So there are subtle differences. Was Dalton knowledgeable of the existence of any of these differences? No, because the experimental evidence of his time didn't show any of those, so therefore he wasn't aware of them. All right, so that was the problem with idea number 2. The problem with idea number 3 is the fact that chemical compounds do exist. Even if you're using definite proportions, they can exist as different materials. So again, the idea from Dalton in idea 3 was if you combine exactly the same atoms together in the same proportion, you must be forming the same material. Well, he did not know that in complex so-called organic molecules, you can connect the same number of atoms together in a variety of different ways of making those connections. We call those isomers. They take exactly the same atoms. In this case, I'm showing isomers of the combination of 5 carbons with 12 hydrogens. They all have the chemical formula C5H12, but the lines are showing how the carbon atoms are connected to each other. There are 3 unique ways in which you can connect the carbon atoms together from these exact same 5 carbons and 12 hydrogens. Now, granted, the differences in the properties of these 3 different connected forms are ever so slightly different. And certainly at the time of Dalton, the, the evidence and the way we looked at things was not high enough resolution to note that there was any difference at all between these three possible ways to connect them. So he couldn't tell that these would have any kind of even subtly different properties. But there are several cases where it should be evident based on the way that they're connected and the resulting properties that gives the materials that ultimately this became discovered. So it turns out that the first three of Dalton's premises had slight problems due to the lack of evidence at the time. They have to be slightly modified. However, Dalton's atomic theory, even to this day, is the main starting point for our interpretation of chemistry. By the way, the fourth item, that in a chemical reaction, the atoms are rearranged and not created or destroyed when you're making the new materials from the reactants to the products. That's pretty written in stone. We can't seem to break that one or say that there's some problem with the fourth one. Just these first three have some slight problems. Okay, now what we're going to do is move some 50 years ahead from Dalton to around the turn of the 20th century, around 1900. And we'll go to this fellow by the name of J.J. Thomson. At the time of 1900, Dalton's idea of the fact that atoms were indivisible, you couldn't break them apart, was still thought to be true. So the chemists of the time, around 1900, for about 50 years now, had believed in atoms, but had believed that you couldn't take atoms apart. Well, what happened around 1900 in the lab of this individual, J.J. Thomson, was that he was able to put sheets of gold into a very powerful electric field. And in a powerful electric field, you have a separation of positive charge from negative charge that drags and pulls on the atoms so violently that it pulls them apart. So J.J. Thomson was able to generate charged beams flowing from originally neutral material by putting them in powerful electric fields. And what he was able to show, therefore, was that there was a subatomic structure to the atoms. He was pulling atoms apart into separate charges. Now, a couple things from Thomson's experiments that he was able to figure out were the fact that part of the charge was positive and part of the charge was negative. So he surmised that the matter started out electrically neutral, and he knew that because when he put them under low electric fields, they weren't pulled toward the plus or the minus. Only when he upped the electric field incredibly high did it start to pull some of the positives toward the negative part of the field and pull the negatives toward the positive part of the field. So he could pull the different materials in a different direction based on their polarity. Now, so original material that is neutral is actually made up of equal amounts of positive and equal amounts of negative. Now, what else he was able to figure out was that the negative was tiny compared to the positive. And how that could be determined was that if you had a beam of negative material in motion, it would curve based on how much it weighs in the field of gravity. Literally, it would start to bend to the gravitational pull, and it could be figured out how much the material or the relative weight of the material based on how it would curve in the field. So he could surmise that certainly the charge on the matter there was equal amounts of the positive and negative, because ultimately it was neutral, but he could tell that the negative was way, way tinier than the positive in terms of mass. So then, in order to come up with a model of this, Thomson purported the so-called plum pudding model to explain how he could have equal amounts of positive and negative charge, but have way tinier amounts in mass of negative charge with much, much more massive amounts of positive charge. He envisioned it as a plum pudding, meaning there was a large pudding of positive charge where most of the mass existed, and embedded here, there, in another place in the pudding were little dots of plums that represented the locations of the negative charge. Now, of course, this is no longer the model that is believed or even accepted, certainly, for how the atom is constructed. And every chemistry book on the face of the earth has a paragraph or two talking about J.J. Thomson got it wrong. J.J. Thomson proposed the plum pudding model. Really, what they should be doing is celebrating the fact that J.J. Thomson was able to understand that atoms were divisible. He figured that out. He figured out that you can take atoms apart. He also figured out that the positive part of the charge was equal in magnitude to the negative part, but that the positive part was way more massive than the negative part. So with this evidence that he had, he could only conclude logically, therefore, that somehow there must be tiny amounts of the negative charge embedded in the large amount of positive charge to make this seem realistic. So what I would like you to remember from this particular discussion is the fact that even though most of the textbooks try to paint J.J. Thomson as the guy who got it wrong, J.J. Thomson was the guy who got it right by figuring out how you could take this thought to be indivisible material and take it apart. Well, we all know that Thomson's plum pudding model was wrong, but how did scientists ultimately determine that it was wrong? Well, there was a fellow by the name of Ernest Rutherford in 1911, and it turns out Ernest Rutherford was an incredibly important scientist. I'll have more to say about him, I guess. We'll do that, I guess, on the next slide. I will. We'll just talk here about what he did. So in 1911, he performed an experiment to test the idea of Thomson. And here's what he did. He also took a thin piece of gold, and he also put it into a magnetic field. And what he did, though, was he shot charged particles at it. And by putting it in this magnetic field, he was able to entice charged particles to fly at very high rates of speed towards the thin gold foil. Now, where he got these charged particles was from radioactive materials. So he had this radioactive stuff, and that's one of the great stories about Rutherford. He was fundamental in figuring out what was happening when elements were radioactive. I should point out to you folks, in the early 1900s, it was probably the most exciting time of physics, because so many new discoveries were being made on such a fundamental level by individuals such as these ones I'm discussing here. But you can't discount Albert Einstein and his contributions at the beginning of the 20th century as well. But just so many incredibly important things were coming about in the realm of fundamental physics and chemistry at that time. But one of the ones, and where Rutherford really was most famous for, was in the area of so-called radioactivity. And very shortly before that, Curie and others, Becquerel, Röntgen, had discovered radioactive materials. And they were just magically emitting energy, magically emitting dangerous particles and energy, and the source of this, why they were doing so, why they couldn't be stopped from doing what they were doing, and what exactly were the types of particles that they were emitting. That was one of the big points of emphasis of the time, and Rutherford was chief among those that was unraveling these mysteries. So Rutherford had this radioactive material, excuse me, and what he was able to do was he knew it was ejecting rather sizable particles out of it. He didn't know what they were. It turns out they were helium nuclei. He didn't know this at the time, but in the course of radioactive elements trying to become stable, their nuclei were falling apart, and as they were falling apart, they were spitting out smaller nuclei of helium. And these didn't have electrons around them, so they were charged. And so he was able to draw them with a magnetic field into a beam, and he was able to shoot very small, but it turned out to be helium nuclei, which he didn't know at the time. But he was shooting these helium nuclei straight at a thin foil of gold at a very high rate of speed. And what was thought was that if the plum pudding model was true, that these things would just slam into the gold foil, maybe bounce back, but if nothing else, gets stuck and embedded in the foil or bounce back off the foil. Well, what happened when Rutherford shot these very, very tiny helium nuclei at the gold foil was that, yes, a large number of them bounced back, deflected at various angles, a large number of them. But also, a very large number of them were able to pass through. Now, some of them passed through almost undeflected. Some of them passed through bent to a certain degree, but that was the amazing thing, that these particles he was sending through somehow were getting through the atoms without any deflection at all. So Rutherford proposed how he could envision it possible that these particles could fly through without bouncing straight back. Now again, many did bounce straight back, but not all of them bounced straight back. So the idea was, why did they sometimes bounce straight back where other times they didn't? So Rutherford was puzzled by what he saw. Some of them, of the projectiles he launched at the atoms, would bounce back, but many of them could pass through, some mostly undeflected at all, some of them bent slightly. So what Rutherford then envisioned was that maybe atoms had what he called a planetary structure. And what we mean by a planetary structure is referring to our solar system. There are a number of massive objects which can fly through the solar system without ever striking any object in the solar system, because there's vast amounts of space, even though the planets themselves, and of course the center of the solar system is a very massive object. The solar system is dominated on its scale by empty space. Well, he proposed the same thing at the atomic scale. He proposed that the atoms were like the solar system. Atoms were mostly empty space, At the center of the atom was the positive charge, which kept the negative charge, tiny, small satellites of negative charge, in motion around the massive center. Now, see, what holds, of course, our solar system together is the gravitational pull of the sun to the planets. But here, what holds the atom together is the electrostatic pull of the opposite charges of the electrons and the protons. But in any event, much like the solar system itself, there was a huge amount of space that allowed for these smaller atoms that he was shooting at the gold foil to easily and readily pass through the big, vast empty spaces that existed in each atom. Now, what this conjecture meant was that, first of all, it was met with a lot of skepticism, and the main skepticism that was purported to the planetary model of Rutherford was the fact that, wait a minute, we know this so far. We know there's a large number of elements. We know that elements of different atomic types have different amounts of this positive charge in them. So we know that gold has a lot more positive charge in it than does hydrogen, for sure. And you're purporting that this much more massive amount of positive charge in in gold compared to hydrogen can all be concentrated at a center. How can that possibly be? Because the positive charge of all these individual so-called protons that carry the positive charge have to be repulsive to one another. So how can you pack protons together in this region that you call a nucleus? And Rutherford's answer was he didn't know, because no one had ever seen or even dreamt up the nucleus before this. Rutherford proposed there must be some other material in there acting as the glue to the nucleus. Because what else was becoming available was knowledge of the ratio of charge in the nucleus to the surrounding electrons. They could tell from experiments that they were performing just how heavy a various amount of charge happened to be. So of course they knew that protons were very heavy compared to electrons, but there was also some sense that there was some other mass at play in the nucleus other than the mass due to the positive charge. So what Rutherford proposed was there must be a third subatomic particle that resides where the positive charge is located, or that resides in the nucleus. He proposed that this third subatomic particle could not have charge associated with it because it wasn't detectable by placing and accelerating a destroyed atom in a positive or negative electric field. So there was no way using charge tricks to attract this third subatomic particle because it had no charge associated with it. He even called it a neutron. So the neutron has no charge associated with it, and it's roughly this. You could determine it was roughly the same in mass as the proton, and both the proton and neutron were way more massive than the negatively charged electrons. So his planetary model provided for an ability for the positive charge to all be centrally located, provided that neutrons were present with the protons in order to hold and glue the nucleus together. Modern theories now seem to point to the fact that neutrons are in some way protons married to electrons in some way. Again, Rutherford proposed the existence of the neutron. They were very shortly thereafter subsequently found. So Rutherford's planetary model of protons and neutrons, very massive, packed into the nucleus, surrounded by orbiting tinier electrons, became the accepted model of the atom. So all the textbooks will show you Rutherford's planetary model of the atom, and it's pretty much the model of the atom that we go with when we're thinking about the behavior of an atom. Well, I got bad news. Rutherford's planetary model doesn't work either. And why Rutherford's planetary model doesn't work is the fact that if you have electrical charge of the electrons in motion around the nucleus, and if you think of it in circular orbits around the nucleus, when charge moves circularly, it must accelerate to maintain a circular path, meaning it's changing speed. More correctly, it's changing velocity to stay in a circular path. It's the only way it can stay circular. Changing its velocity means it's changing the direction of its motion. As it changes direction of the motion, that's an acceleration, charge caused by the attraction between the electrons and the protons. Well, accelerating charges are known to radiate. So this should be giving off some radiation as it's doing so, and as it gives off radiation, it gives off energy. And as it gives off energy, it will not be able to move as quickly, and it will slow down, and that will pull it in closer and closer and closer. So what would happen is eventually, if it was accelerating inward, it should crash onto the nucleus. So there are definite problems with the planetary model as well. We will try to rectify Rutherford's planetary model problems later. For now, what you should go with is the planetary model. Everything we talk about for the next week or so will be based on the planetary model. Later, we'll try to correct it so that we can build the modern picture of the atom when we get a little more ammunition under our belts. Okay, let's talk a little bit about the subatomic particles, the proton, neutron, and electron. First, let's begin with the fact that two of them are charged and one of them isn't. The proton and electron there are listed with their charges in the SI unit of charge known as the coulomb. Now, what you should be remarkable about these numbers is that they're tiny. Each of these subatomic particles possesses a tiny, tiny, tiny amount of charge, listed there as 1.6 times 10 to the minus 19. Now, this is a measurable amount of charge, so being measurable, it should be determined to more than 3 digits of accuracy, which it can be. As a matter of fact, it's probably known to 10 digits of accuracy. And believe me, you have to work really hard to figure this number out to 10 digits of accuracy. But having said that, what I would first point out to is that the digits of the magnitude of charge for the proton and the electron match each other to the limit of our ability to measure. So they match each other exactly in all digits of measurement. And as a matter of fact, theoretically, it is predicted that the charge on the proton and the electron is exactly the same in magnitude to all digits of measurement. They carry what is known as the fundamental unit of charge. According to our understanding, this is the smallest amount of charge in the universe. What this means is you can't take a proton and electron and then take a cleaver and cut it in half, and so one piece of it would have half that amount of charge and the other piece would have the other half of that amount of charge. This is, as far as we understand, the smallest amount of charge in the universe. All other charge is just built up from this. So as a matter of fact, then, if you had 2 electrons, they'd have a charge of 3.2 times 10 to the minus 19 coulombs. If you had 4 electrons, they'd have a charge of 6.4 times 10 to the minus 19 coulombs, and so forth. So essentially, you can build up any real number charge unit by adding up these ridiculously small charge units. Next, and even weirder about protons and electrons, is that the sign of the charge is displayed as opposite. The charge on the proton is plus 1.6 times 10 to the minus 19 coulombs. The sign on the electron is minus 1.6 times 10 to the minus 19 coulombs. What the implication of the sign is I would prefer to call this the flavor of their behavior. Meaning, suppose you take a third charge and you place the proton near that third charge. Due to the action of electrostatics, the proton will either be attracted or repelled by that third charge. So the proton will either move towards that third charge or away from it. And it depends on what type of charge that third charge is. As I think we're all aware, like charges repel, opposite charges attract. So if you put an object of the same sign charge as the proton near it, it will push the proton away. If you put an object of opposite charge to the proton near it, it will draw the proton towards it. So the nature of what the sign is doing essentially is telling you whether you are having repulsive or attractive, either push or pull, relative to a third charge. So that's what really is going on with the assignment of the plus and minus. It's trying to indicate with some kind of numeric significance what kind of action this charge will take in the presence of another charge. So that's indicating a difference of the type of behavior of these individual charges by putting that sign in front of them. Is an electron really negative compared to a proton being really positive? That's not what this is trying to connotate. What it's trying to connotate again is that one will be pushed to the right, maybe in the positive coordinate frame, while the other would be pulled to the left, which we could say is negative direction in the coordinate frame. That may be a little more correctly the way to think of it. Now let's turn to the mass columns for these particles. First, it should be noted that the electron is way, way less massive than either the proton or the neutron. The mass of the atom is essentially, not entirely, but almost entirely concentrated in the nucleus, where the protons and neutrons reside. As a matter of fact, electrons are a little more than 1,800 times lighter than either the proton or the neutron. Way, way smaller in mass. Now, the next thing to note is that to the first 3 digits of accuracy, the mass of the proton and neutron are exactly the same, but when you get to the 4th digit of accuracy, it turns out the neutron is a little smattering heavier than is the electron, out to the 4th digit of accuracy. Essentially, at least to small degrees of accuracy, protons and neutrons weigh exactly the same. When you get really close and careful at examining them, the neutron is slightly heavier than the electron. And one of the points as to where and why a neutron is slightly heavier is that what we now understand is that a neutron in some way is a proton fused to an electron. They are married together. So with a little bit of mass defect due to the energy of shoving them together with the formula E equals mc squared, as a matter of fact, they don't the sum of the weight of the electron and proton doesn't exactly equal the weight of the neutron, again, because there's some mass defect for the energy of holding them together. But essentially, electrons and protons married together do make neutrons. You can actually break a neutron down. That's what happens in a wide variety of radioactive experiments or processes where electrons can be ejected from the nucleus as a neutron decays into a proton and spits out its electron that was carrying in it. Okay, so do I expect you to really know these numbers off the top of your head? No. But what I do expect you to know is that because the proton and electron have the smallest amount of charge possible, and because they are opposite in sign to one another, rather than remember that cumbersome number, you should remember the more easily designated number in chemistry, that the smallest amount of charge is just assigned to be the value 1. And so protons from now on, since they're the positively charged smallest amount of charge, we're just going to call it +1. Electrons have exactly the same magnitude of that charge, just opposite in sign. So from now on, we're going to assign to the electron, instead of negative 1.6 times 10 to the minus 19 coulombs, I'm just going to call the charge on a proton from here out -1. So when we make cations or anions, as we will see very shortly here, we will make them charged in integer units, moving the charge up or down by 1 unit rather than moving the charge up or down by 1.6 times 10 to the minus 19 units. Let's show some ideas regarding the origins of symbolically representing atoms. On the top here, I show some of the Greek representations of various elemental forms, and below that I show the European representation of elemental forms. First of all, not all of these are elements. Let's get that straight. Matter of fact, if you look at the Greek things, only tin, sulfur, silver are technically atoms. The rest of these things are just, gold is also symbolized there as well. The rest of these things are just part of the symbolic representation that was used by the ancient Greeks when they were writing down recipes that they would use for keeping track of how and what they were mixing together to make various poultices and compounds and things that they might be doing. Same thing is true with the European symbols I'm showing below. These are the things that would have been being used by the alchemists. Mercury and arsenic are certainly elements. The other things are water, of course, isn't, and all these other things that we're seeing there, none of them happen to be elements either. However, here's what I want you to take from this representation. So the bottom ones are, say, what the alchemists would use when they're representing, they're keeping track of their recipe and their procedure for how they will carry out some chemical process. Remember, it's possible that an alchemist was sort of like a wizard or magician of the time, trying to travel from fiefdom to fiefdom to show, give a demonstration, a public demonstration, to entertain or frighten people, to gain access to the lords of the place, and to, in some way, gain power. So let's suppose you had a recipe to make a mixture that you could put in your hand and then put a spark to it, and it would explode and make a puff of smoke. And it would frighten the crowd or entertain the crowd or in some way give you an advantage towards what people perceived of you. Would you want to write it down in an open way, the recipe that you used, You write it in these using these cryptic symbols so that the secret of your technique is secret. Nobody can read your recipe because of these cryptic symbolic representations you're using, so nobody else could duplicate your process and spill the beans as to how you're doing it or gain the same favor for the trick that you're performing compared to what they're performing. So the origins of representation of the symbolic writing of these things are necessarily cryptic, to keep it a secret as to what you're doing compared to what your competitors might be doing. And also then, if you look at these and say you would happen across a book full of these recipes and concoctions and things, and you began to look at it, it certainly would have devious, satanic even appearance when you would see a book full of these cryptic intonations and incantations written in these crazy symbolic ways. So that further enhanced the idea that these people were doing secretive things that might not be holy or might be thought of as being dangerous just by the nature of how they were being represented with these early symbolic forms. Now, do I expect that you know these symbols or anything like that? No, we're just here talking about what was the origin and history behind the way these materials and the processes behind these materials might have early on had been symbolized. So I don't expect you to know any of these off the top of your head. Let's jump ahead a little bit and look at the time of Dalton again, around the mid-1800s, early 1800s, and let's look at the symbols that were being used to represent chemical processes during that time. Now, I will admit they are still cryptic in regard to them not being transparent as to what they represent, but I will point out that now they are in some way becoming a little more systematic. Let's, for instance, look at the symbol representing hydrogen and the symbol representing oxygen. What you should now notice then further down the page is how chemists at the time of Dalton would have represented water. It was a combination of hydrogen and oxygen. You should also look at how they would represent ammonia. Ammonia was a combination of hydrogen and nitrogen. Now, one thing I want to point out is they got the formula of water wrong. We now know it's H2O, so that's a little incorrect. We also know ammonia is NH3, so the way it looks like they're symbolically representing it would be NH. So they were a little bit off in their symbolic representations, but that you can at least see by this time they are now being at least beginning to systematize and understand that the combination of certain of the building blocks could be used to make some of the more complex materials. You might notice carbonic oxide was what we would now call carbon monoxide, and carbonic acid is what we would call carbon dioxide. Sulfuric acid looks like SO3. Well, interestingly, if you dissolve carbonic acid, what they're showing is carbonic acid in water, which is really H2O, you would get the formula of carbonic acid, H2CO3. If you take what they're representing as sulfuric acid and put it in true water, which is H2O, you'd get H2SO4, which is the actual nowadays accredited formula for sulfuric acid. Now, once again, do I expect you to know these symbols and what one's what? No. Again, here what we're trying to do is simply show the evolution of representation of the symbolism of understanding and representing elements and the combinations of elements in multiple or definite proportions, how we are evolving in science and showing that this can be symbolically represented. Still, at this time, it's pretty cryptic because you can't really tell what's what based on these particular symbols that they had chosen. Let's show some modern atomic symbols. And of course, now we're all about transparency. We want you to immediately be able to understand what we're attempting to represent. So instead of writing out the longhand traditional names of the various elements, every one of them is given a chemical symbol. Most of these chemical symbols are chosen for logical reasons. For instance, here we show very familiarly the chemical symbols of element 1, 4, 7, and 8. Hydrogen, helium, nitrogen, and oxygen. Certainly hydrogen, nitrogen, and oxygen are among the first of the identified chemical materials that existed in nature. So they got the original, they were named, and then their symbols were taken straight off of their name's first letter. Now, of course, for helium, since H already got, hydrogen already got H, helium had to be adjusted in some way, so it was adjusted to be helium. So the point you should take from this slide compared to the previous slide and the previous slides was that the evolution of representing symbolically chemical materials was that it went from some cryptic trying to hide and keep secrets from each other into something that was becoming transparent, or at least systematic in the way it could be used to represent combinations of the building blocks, into now something that is completely transparent that we can now use intended as a shorthand notation for transformation between various elemental forms to form more complex forms, or at least undergo chemical change into new forms. This slide is simply trying to show you that as science progressed and more elements became known, that we became more creative in where names were given to the various elements, and particularly for the heavier elements that have either most recently been manufactured in laboratories or don't even really exist naturally in nature, or are such rare elements that if they did exist in nature, they are present in such small amounts that they just weren't commonly used for quite some period of time. Now the scientists who discover or form them have the latitude of helping to give them a name. Many of them were named for places, like PO was polonium, named by Curie for her home country. There's an element, berkelium, named for the scientists at Berkeley who manufactured that element, and there's many other. There's americium for the element discovered in America, or actually built in America. So there's names of that type, but there are also a large number of names of elements that are reserved for some of the most celebrated of all scientists of all times, like Einsteinium, fermium, curium, and there are many others as well that were given names in honor of some of the most important scientists of all time. Some of the symbols of elements come from their maybe German or other names of that type. Like, for instance, I would point out the symbol for tungsten is W, where you might say, how in the heck did tungsten get W? Well, in Germany, tungsten is known as Wolfram. It starts with a W, so they gave it the symbol W. As a matter of fact, I should point out, in England, aluminum, which is the symbol Al, is not even called aluminum, it's called aluminium. So that's kind of weird, but that's what it's called. But what I'm showing on this slide is the fact that many of the elements, and a large number of them as a matter of fact, have their symbolic representations given to them that result from their original names from either the ancient Greeks or, in this particular case, their Latin names for that were used by the Romans. Copper was known as cuprum, so its symbol is Cu. Gold was known as aurum, for aura or whatever, aurum. So the gold still to this day is symbol Au. Iron, ferrum, Fe. You see there I have also silver, which was known as argentium, like Argentina, where it was actually mined for a long time. So that's the symbol Ag. Tin we see was known as stannum, so ultimately became the symbol Sn that was used. And lastly, I want to point out the symbol for lead. Lead in modern chemistry discussion is always represented by the symbol Pb, and that comes from the Latin name for lead of plumbum. Or plumbum. I'm not quite sure how to say that in that regard. But what I would like to point out is the story behind lead. And the story behind lead is the fact that if you've ever encountered lead, you would know that it's a very malleable and ductile material, meaning lead can be easily shaped and formed. And as a result, early artisans were able to fashion a wide variety of objects by bending and shaping and forming lead. Well, in ancient Rome, as the civilization of Rome grew and grew, what became very popular among the rich and powerful was a desire to have indoor plumbing. So all the rich, fancy people wanted their homes so that they didn't have to go outside to go to the bathroom, but more importantly, they wanted well water pumped directly into their homes. So they didn't want to have to go outside and tote a bucket of water into the house. They wanted to open a pipe, turn on a spigot, and have the water flow through the pipes in their house. Well, based on its malleability and bendability and shapeability, the most utile, and its ready availability, the most utile material to make piping in ancient Rome was to use lead. So what became in vogue, in fashion, and very status symbolish was for the rich and powerful people of Rome to put indoor plumbing in their homes and fashion that indoor plumbing from lead. So this included all the richest merchants, all the important military leaders, of course the important nobles and ruling class, the important members of the Senate. All these people had indoor plumbing made of lead put into their homes. Well, of course, if you know the story of lead, turns out that it's not very, doesn't jive very well with living systems. Lead poisoning is a very serious issue, and if you run water long enough through lead pipes, you're going to get lead ingested or infused into the water, and then ingesting that water turns out to be not a good thing. Certainly not for the progeny of the rich people for sure, but even for the people themselves. So one of the urban legends of the downfall of the Roman Empire, including the fact that it got too big, including the fact of the changes in religion and all sorts of other things that went on, including also the invasions from the outside edges of their extended empire that they could no longer control. But another factor that many people cite is the fact that the rich people wanted indoor plumbing, and they made their indoor plumbing out of lead, so it led to a weakened elite class of the people in Rome. Now, another and final note here is that notice the name for lead in Latin form. It's plumbum, and again, as I mentioned, lead was used for the plumbing in the homes of ancient Rome, and you can see where the word plumbing comes from based on its use in these pipes.